I need, all right, here it is. All right, yeah, thank you. So here's the outline. I'm not going to talk anything about land impact because Mark Boslow covered some of this yesterday. All right, so that's the motivation. I'm going to talk a little bit about the numerical framework, background on entry impacts, and then I will do the impact on the ocean and some consequences on the east and the west coast of the United States of America. We're all motivated. Let's skip these. So here's the framework. So we discovered there is a gap actually in doing water wave coupled with hydrocodes. So at the Lawrence Livermore Lab, we decided to build our own water wave code and coupled with the hydrocode. So we create the source, do the impactor, then we carve a box as a boundary condition. We plug it into water wave propagator, and then we can generate some vulnerability or consequences analysis. We've been doing this since 2013. So through the years, we have improved our framework, and we moved from 2D to 3D, from linear shallow water waves to nonlinear shallow water waves. And we coupled through several tabletop exercises the global effect. And I worked with the Goddard Space Flight Center people to do the global climate change. Here's how it works. So we take the 3D domain, we carve a near field domain where we use Geodyne. Geodyne is our impactor code. And then, as I said, we carve the boundary conditions, which are the 6 faces of this box, and we couple to water wave with 3D equations. So I'm giving you here an example of how much cost will take, but most of the time I run all the code in 2D version rather than in 3D, unless I have a highly nonlinear phenomena close to the shore, so I'll switch to 3D. So this coupling actually will allow us to bridge the gaps between microseconds to hours and days, and the resolution from few millimeters to kilometers. Again, this is the code I'm going to use, Geodyne, so it's a highly parallelized code. It does pretty much all what we need for this problem. It has a nice material model library, very rich in the geological part. And actually, we did this coupling with the WPP and SW4, which is a seismoacoustic wave propagation, and we used the same coupling in other domains. So then we decided to extend it to the asteroid problem. We are dealing with asteroid. From my understanding from the exercise from the website is 100 to 300 meters. So what I did, actually, I found out that I did run, assuming the density of 2 grams per cubic centimeters, and I did a few years ago a couple of runs with 250 meters diameter. So actually, the good news is even this exercise is an exercise. Well, actually, it's an exercise of an exercise because those asteroids will not reach the Earth. So like Mark Boslow showed yesterday, here's an impact, it's oblique. So you see the shock tube, it's well developed there. He sees the fireball, I see a ball of steam. And actually we couple this, so most of the energy goes in the gas-water shift and the transformation of the water into vapor, and the vapor will affect actually the global climate change. So again, here to stress is there's like a compressibility, so you cannot just take the hydrodynamic solution and plug it in linear solution, so you need to go far enough in order to hand linear to linear codes. So for water shots or impacts, you need to expect for, say, this was a 100-meter diameter impactor, about 1.5 kilometers to 2.5 kilometers. So about 10 times the diameter of the original impactor, so to reach what we call the linear source. Here's how I'm going to apply it for Paul showed this exercise. So actually, this is PDC 2019. And actually, I participated in another tabletop exercise 2016, which is very close, actually. It's about the same trajectory. So I salvaged a lot of the input files from there. So I assumed 100, 200, and 300 diameters. but actually around 125, 175, and 275 meters. Density is 2 grams, and the trajectory as is. And as you can see, I'm going to put a lot of effort, actually. So I put a lot of gauges so I can monitor the water height profile. This is the trajectory. I would like to bring to your attention the continental shelf, which is going to really behave, impact the directivity of the waves. For example, if you shoot a shot here or impact here, you think that most of the wave is going to be gone this way, but actually it's going to be trapped in this bay, and I will show you some simulations. From the other side, I did pretty much the west coast as well, the Mexico Baja, and then I did also the Hawaiian Islands. So I put enough gauges, about 250 or so. There's the trajectory. This one is the trajectory, and I did some simulations of most of the impacts. So I use 1 square root of the distance to know how far I need to simulate. Closer to the coast of California, the same thing. We put all the stations. This is my blue patch, which is one of the biggest one I've done so far in the last 3 years. And so here's how the results look like. So for example, for 100 meter site 340, it's barely right there. So after half hour, you will see it there, then it gets developed. And then you see the interaction actually of the wave with the continental shelves. Actually, it will decelerate it, but you can see there's more refinement actually of the wave. That's by conservation of energy, because this is deep, this is shallow. When you hit a cliff, you lose height initially, but you gain it by recovering through the energy equation. And you could see after 5 hours, it's pretty much decayed. The water wave heights are plus or minus 1 meter. And I had to dilute actually, or dial down the legend so I can observe the effect, otherwise you will not see them. For an impact 320, which is closer, even closer to the continental shelf, you see more actually interaction with the continental shelf. But again, after 2.5 hours, 5 hours, it's pretty much decayed. There is some resonance here, and again, this whole bay, there are a lot of waves that they get trapped, and I will show you for the 300-meter diameter, you will see it even better. Here it is 100 meter. No, it's above or on top of the continental shelf. And I did not do these because you have to do them in nonlinear hydrodynamics, so I had to switch back because there is no enough water depth in order to, so if you use it just a shot right there, you will dewater the water or the ocean. So I had to run them all in nonlinear regime, and I will show you the results. But again, you see the resonance. So even though it's here, you think it's going to go directly to the Manhattan Island. Actually, most of the energy get trapped there. For 100, 200, 300, so I just took some snapshots at quarter, 3/4, and 1 hour and quarter to show you how they are developed actually. And beautifully, you see the interaction actually of the water waves with the continental shelf, and that's what we call the Van Doren effect. So, so again, they look like a filter of one of each other. So this one is a 300, has more energy, has a higher water wave in the beginning. And so that energy is sustained to further distances, and that's why you see more resolution here than the other. So if I take that whole, line of stations, and I will develop it, so from 144 to 477 gauges, and I pretty much put roughly where the states are. So Florida, Maryland, New Jersey, New York, Connecticut, Rhode Island, all these levels. So, and then I took all this simulation, get the min and max, and you see how the difference actually look like. And then, and you can see actually there's no linearity between the runs. So if you put 400 meter diameter, actually the water wave will not be much higher than 300 meters. So there's a diminution in the ratio between the waves. So if you take this as a threshold, you can generate like a hazards map. So the green are safe, the yellow are an alarm, and then the red you have to evacuate, and you can produce those as much as you want. Then we looked at the East Coast actually, and this is a zoom around I think shot number 8 and number 14 around the Hawaiian Islands. And I did similar results. I'm not showing the 300, but you can reach water height of as high as 15 meters because those are very close to the Hawaiian Islands. So it's about location and bathymetry. That's what drives literally the water waves. Voila, and I will take any questions.
Thank you very much. Anybody have any questions? We got a little time for 1 or 2 questions. No? Okay, thank you very much, sir.